So in chapter 3, we start looking at some of the basic characteristics of elements and compounds, and we're going to begin by looking at the elements. So, elements are pure substances that are made up of identical atoms. So in a sample of an element, there's only one type of atom present. There are 118 known kinds of atoms. We recently completed the periodic table. You might see some older periodic tables that don't have the last few elements on there. That's okay. We're not going to really be using those elements that are at the end of the periodic table that are all radioactive. Each element has its own symbol. The first character in an atom's symbol is always an uppercase letter, and it's important to get that correct. Most of the atoms on the periodic table also have a second character in their symbol, and that always has a lowercase. Now, you want to be careful with this whole case business, and sometimes our writing needs to be sort of like modified slightly to make things clear. So a good example of this is if I write uppercase C, lowercase o, that is the element cobalt. But if I write uppercase C, uppercase O, that is the compound carbon monoxide. Now, you might not think that this is particularly significant, but if I had, a kilogram of cobalt sitting in my lounge room, I would be completely safe. Cobalt is a solid. Unless I dropped it on myself, it's not going to do any harm to me. However, if I had a kilogram of carbon monoxide in my lounge room, I would be most certainly dead. Carbon monoxide is a colorless, odorless, deadly gas that fills any container that it is placed into, and so I would end up breathing in that carbon monoxide, and at that kind of amount, it would almost certainly be lethal. So we do need to be mindful of the case of the characters that we're using. So here we go. This is the symbol for calcium. This is the symbol for potassium, and this is the symbol for strontium. This is the symbol for tin. That's the symbol for titanium. This is the symbol for tungsten, and finally that's the symbol for sodium. So what you realize is that some of the elements, their symbol seems to be directly related to their English name, right? Seems to be, very kind of similar to the English name. And then others, so we've got potassium here, tungsten, tin, and sodium, and the symbol seems to have no connection to the English name. So we do want to be a little bit careful about not to, we want to double check that we've got our symbols correct rather than assume that we've got them correct, because they're not always obvious. There are about 11 symbols on the periodic table that are derived from Latin or German, and that they don't bear a connection to the English name, and we need to be a little bit careful with those. Particularly potassium causes an issue. People confuse it with phosphorus, which has the symbol P. Okay, so in addition, each element has a name as well as a symbol, and you want to be aware, like I said, that the names of some elements and their symbols are often different. Potassium is an example, tungsten is another one, sodium is another one, lead, tin. There's a bunch of them, like I said, 11 of them that have no connection to the name in English. You probably want to look up and bookmark a list of atomic symbols and names in alphabetical order. That can be really, really useful. So find a picture that looks like this, that has all 118 elements there with the symbols and the names next to one another, and then a bookmark that. Remember, everything that you're going to be doing in this class will be open notes, so you can use all of your resources. So you want to have your resources bookmarked and ready to go for when you're doing those quizzes, tests, and exams. Okay, only 88 of the known elements actually exist naturally. The remaining 30 have all been made in the lab, and they don't exist for very long periods of time. They are all what we call radioactive. That's why we're not too fast if your periodic table is a bit of an older one and doesn't have like the last 4 or so elements in it. Now, it turns out that the universe is pretty boring. While there are 118 elements, most of the matter in the universe is only of one of 2 types of atoms. It's either helium or hydrogen. And it's even more boring than that. Most of the universe is, greater than 90% of the universe is hydrogen, and almost 10% of the universe is helium. In fact, it's less than 0.1% are any other atoms. And so that's kind of interesting. But also what's interesting is, how the heck do we know this? How do we know what the universe is made of? I mean, apart from the occasional, space rock that falls from outer space, how do we know what the universe is made of? And it's actually quite clever. What we do is we look at, well, what do we get from space most commonly? The thing that comes to Earth from space most commonly, of course, is light. And it turns out that when you energize an element, it tends to glow with a characteristic color. And for example, a good example of this is if you energize neon, it glows with this nice pink color. And you probably know that if you heat up a piece of iron, it glows kind of red hot. It glows a kind of orange color, right? Well, when you look at the lights coming from stars, guess what it looks like they're made of? A glowing ball of hydrogen with a tiny little bit of helium in it. Now, you might have noticed that some stars look a little bit blue and some stars look a little bit red. If you're lucky, you might have seen that through a telescope. And we can actually distinguish the different compositions of different stars on the basis of the color that they glow. It's kind of fun. Now, if I look at the Earth's crust, it's kind of boring too. 80% of the Earth's crust is made up of 2 elements, silicon and oxygen, forms what we call silica or silicates. A good example of this would be quartz. And then there's a handful of other elements that make up the rest of the part of the Earth where, things live. So if you look at the crust, the atmosphere, the oceans, all of the waters on the Earth, 80% of it is just made of silicon and oxygen with trace amounts of other stuff. So the elements are not evenly distributed across the universe. And if you look at what humans are made of, if we look at what we're made of things like carbon, hydrogen, and oxygen. They're our biggest components, right? So it's different from the crust and it's different from the universe at large. Now, most elements are found in nature as individual atoms. In fact, all but 9 elements are always found as individual atoms. So what happens is, if I have a collection of carbon atoms and 2 carbon atoms bang into one another, they don't get stuck to one another, they remain as individual carbon atoms. However, 7 elements are always found in nature as what we call diatomic molecules. That is, there's 2 atoms stuck together to form a single unit. And these are hydrogen, and then we hop on over to number 7, which makes it convenient to memorize. When we draw a 7, we get nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So whenever 2 hydrogen atoms bang into one another, they stick, and then we make what we call an H2 molecule. Now, if another hydrogen atom comes in, it doesn't stick. It just kind of bounces off, right? Okay, so hydrogen atoms always kind of seem to pair up, but they don't get any bigger. Same with nitrogen atoms, oxygen atoms, fluorine atoms, chlorine atoms, bromine atoms, iodine atoms. They're always found in nature as these pairs of 2 atoms stuck to one another. Now, similarly, phosphorus is always found as P4, 4 phosphorus atoms stuck to one another. Not 5, not 6, not 2, but 4, right? And sulfur is found as S8. And S8 is kind of interesting. The sulfur atoms are actually joined together in a ring, which is kind of cool, right? So I see if I can draw it. But they kind of you get 8 of them joined together in a ring. 1, 2, 3, 4, 5, 6, 7, 8. And they join together in a ring. And it's just kind of really weird. It's kind of fun. Okay, so most of the elements exist as individual atoms. When they collide with one another, they don't stick. 7 are found as diatomic molecules. They pair up. And then phosphorus and sulfur are P4 and S8. They form larger connections of atoms stuck to one another chemically. So you need to know that. You need to know what the diatomic 7 are, and you also need to know that phosphorus is found as P4 and sulfur as S8. So just going through the diatomic 7, they are hydrogen, and then you go over to number 7 and you draw a 7. There's another way of remembering it. You can remember the phrase, have no fear. Have no fear of ice cold beer. So that's the Australian method, okay? So that's another way. So between the 7 and the have no fear of ice cold beer, you should be able to memorize these guys. All right. You will need to know the physical state, that is whether the elements are solids, liquids, or gases under standard conditions, so room temperature and normal atmospheric conditions. So this sounds kind of a bit daunting, but it's not actually that hard. And the reason is because most of the elements on the periodic table under standard conditions are solids. So let's work on, if you just remember what aren't solids, then everything else is a solid. So bromine and mercury are liquids at room temperature. And then we're going to go hydrogen, nitrogen, oxygen, fluorine, chlorine, and then helium, neon, argon, krypton, xenon, and radon are all gases at room temperature, and then everything else, all of the other guys, are solids. Okay? So if you can find or bookmark a periodic table that has these, I color-coded like I've got here, then you don't have to worry about memorizing that. You just have to make sure you double-check it if you need to know the physical state, okay? So it's not about memorizing it, it's just about being mindful of the fact that they do have different physical states at room temperature and having that information at hand should you need it. But it's also a pretty easy thing to remember. All right. So, along with getting a list of atomic names and atomic symbols in text, it's sometimes useful to get a periodic table that has both the symbol and then underneath the symbol to have the name. So if you can find an image on the internet or a web page on the internet that has a periodic table that looks like that, that's going to really help you out because you're going to get familiar with where things are on the periodic table, and it's easier to use than using just a text table. It's also worth, you can kind of like always label your periodic table. So, people will draw in the diatomic 7, people will circle the ones that are gases, people will kind of like, or they'll shade things and stuff. So, getting used to using the periodic table and finding those different versions of the periodic table is a useful thing to do. So in this question, you're asked to fill in either the element name or the element symbol that is missing, and it's a pretty easy thing to do with this periodic table. So we've got C for carbon, so that's going to become carbon. Calcium, you've got to find calcium, there it is, it's Ca. Nitrogen, it's over here, it's uppercase N, the case is important. Mercury, it's one of those ones that has a weird symbol. Here it is, mercury, Hg, very, very toxic, neurotoxin. Element name, iodine is the symbol over here, iodine, I know these so well. And then He, there it is up there, helium. So you just got to find the information to do that kind of problem. Just basically don't make a mistake. All right, here's another one. H is for hydrogen. Ca, we already had that one. Calcium. C, it's over there. Carbon. Just don't make a spelling mistake on these. Ag is another one where the symbol doesn't align with the English name. It is silver. Copper, Cu. get the case right, and then chromium in the same row as copper, Cr. Okay, so there's a couple that, you know, like I think I see people getting caught out on. There's a whole bunch of R ones. So we've got rubidium, radium, radon, and then there's rhodium, ruthenium. You just kind of a little bit of care there. I think, you know, it's worth mentioning that. Okay. Now this one, it says, write a complete chemical formula including the physical state symbol. So we need to talk about that. So if the physical state is solid, we indicate that by putting parentheses S after the element symbol. If it is liquid, we put parentheses, you guessed it, lowercase l. And if it is gas, it's parentheses lowercase g. So you have to remember what are solids, what are liquids, what are gases. Something to be aware of is if you just are drawing a blank, always put solids because the odds are in your favor that it's a solid. So the first one here was done for us, and then we have to do for the next one. So lanthanum, I'm just going to find lanthanum in my table. The symbol is uppercase LLA, and it is a solid. So what are my liquids? Mercury and bromine. It's neither of those two. And then my gases are hydrogen, nitrogen, oxygen, fluorine, chlorine, helium, neon, argon, krypton, xenon, and radon. And it's none of those, so it's got to be a solid. Okay, Xe is for xenon, Xe. And then xenon is a gas. So the gases, again, hydrogen, nitrogen, oxygen, fluorine, chlorine, and then helium, neon, argon, krypton, xenon. There it is, right? So it's a gas at room temperature, or what we call standard state conditions. And then iodine, you got to remember for iodine, it's one of our diatomic 7. Right, our diatomic 7. Have no fear of ice cold beer. It's the ice. So we have to remember that it's I2, and iodine is a solid at room temperature. Iodine is a solid at room temperature. Now this is a lot of information to memorize, and I don't recommend that you memorize it. What I recommend is that you have the information available for you to look up while you're solving these problems. You'll slowly memorize it as time goes on, but to begin with, you just want to be making sure that you've got this information to hand rather than have it memorized. That's why your notes are really important. All right, let's go again. We've got carbon. Element symbol for carbon is an uppercase MC. It's a solid. Plutonium, it is Pu. It is also a solid. And then fluorine, we've got to be aware of this. Fluorine is one of our diatomic elements. It is F2, have no fear. It's the fear, have no fear of ice cold beer. All right, so it's F2, and fluorine is a gas. F2, gas. So there's a lot going on to get these guys correct. Okay, let's go again. All right, so that concludes this first section on the elements. What are some tasks for you? We need to know what are solids, what are liquids, what are gases, and we need to know P4, S8, and the diatomic 7. Okay, and then we need to be able to kind of like, we also need to know how to assign symbols and names. All right, I hope you found the video helpful, and once again, if you have any questions, please just let me know.